Greetings. Welcome to my second presentation looking at wood as a structural material. In this presentation, we're going to talk about moisture content in wood, a very, very important topic that affects its structural performance capabilities. We'll talk about compressive and bending strengths, specific gravity, and density, a very big factor that tells us a lot about how we could expect wood to behave. Hardness, brittleness and ductility, and bending and bearing strength as well. Okay, just a quick review of some vocabulary, very important to describe the geometric properties of timbers and boards. So we have longitudinal, radial, and tangential. So longitudinal is cut along the length of the tree trunk. Radial would be coming from the center. So if we cut a cross section, like here, we cut a cross section and we're looking into the longitudinal axis. So this is the longitudinal axis in this direction. And if we cut a cross section through it, and then the radial direction would be stemming from the center of the trunk outwards. And tangential is cut like tangent to the rings. And we could see it here as well pretty clearly. So there's our circular growth rings, and tangential cut would be cut just as our basic high school geometry, that a tangent is a line that just runs along the edge of a circle. So likewise, a tangential cut is tangent to the circular growth rings. Okay, so when we describe wood and how it's cut, timbers, the lumber, we have to understand how it relates to the trunk, to the original tree trunk, how it was, the direction that it was cut. Okay, moving on to moisture content, very important. So moisture exists in wood either as a bound water that is held chemically within the cell, or free water that is stored in the cell cavities. And we could see that here. So here we have the bound water, and then within the free water, here is in the cell cavities right there. Okay, as freshly cut or green, so green wood or green timbers are ones that have recently been cut and they're still have a lot of moisture in them. So as they dry out, the free water evaporates first, and that's what we see happening here. So these white spaces, that's the free water that's now dissipated. So the fiber saturation point is reached when all that free water is gone, leaving only the bound water in the cells. Okay, and then this third diagram here shows that the wood has actually shrunk from 4 to 8% of its original volume has actually shrunk because of that loss. Okay, we can see that these cell walls here have tightened up around the cell cavities, and that is where the shrinkage occurs. All right, the fiber saturation point averages about 28% moisture content. All right, so once that moisture is gone, we're at about 28% moisture content. All right, when it drops below the fiber saturation point, the wood begins to shrink, undergo changes to its physical and mechanical properties. Very important, it becomes stronger. All right, so that's what we're looking for, is that we want our timbers to have reached that point. All right, moisture content of wood fluctuates in response to the changes in the relative humidity of its environment. All right, and here's a simple chart of the United States talking about the average moisture content in different parts of our country. So of course, the United States has a lot of different the weather and the climate it varies greatly across this big country. So understandably or not surprisingly, the average moisture content also changes a lot, from here in some drier areas down to 6%, and then tiny sliver here of California, but here in the southeast up to 11% moisture content. Okay, as relative humidity increases, the amount of bound water increases and the wood expands, and as it drops, the bound water decreases and it shrinks. So anybody that has an older house with old doors or windows would know this. When humidity is great, our wood doors and windows would stick. So that is kind of intuitive. Equilibrium moisture content is reached when wood is no longer gaining or losing moisture. It has reached equilibrium with its environment. That's a very important state that we want to get to. It's very important for like flooring, for instance. So often specifications will say that when flooring is delivered to a job site, wood flooring, it should sit in the building for about 2 or 3 days so that its moisture content is at equilibrium with its environment. And that means that when it's installed, it's actually very stable, and we wouldn't expect it to be gaining or losing moisture in any significant fashion that would cause stress within the wood and perhaps buckling in the floor. So we want our timbers or wood, whatever type of product, if it's framing or it's a finished product, to be at equilibrium with its environment. All right, and here is the equilibrium moisture content, different parts of the country. So this is just kind of just interesting. So if we just quickly go down, actually I think it is Juneau in Alaska is actually, I think, one of the greatest numbers here at 18%. Just skim down here quickly. We see some others that are also in Oregon, up in the high teens. So yeah, a lot of northwest cities perhaps have particularly high moisture content, not surprisingly. And then if we go down to Arizona or Las Vegas or El Paso, is that El Paso? Yes. Then we're down in single digits. So again, depending on where a project is located, obviously these numbers change greatly. Okay. All right, so dimensional changes. Wood is dimensionally stable above the fiber saturation point, but below that point it shrinks and swells. Okay. This movement is greatest in the direction of the annual growth rings, that tangential cut that I was describing. All right. About 1/2 as much across the rings and much less longitudinally. So as this wood is changing, it changes in relation to the grain. Essentially, we would call this the wood grain. So longitudinally, if we were talking about a column or a stud in the vertical direction, it's negligible, the change. But here we see much more significant changes, tangential cuts. So that would be this direction right there, and that could affect flooring, of course. That's when flooring would be opening and closing and creating gaps in that direction. Okay. And this diagram shows this reinforces that point and returns to my earlier presentation where we talked about the different types of cuts relative to the growth rings. So here is our quarter sawn lumber, right? Our premium lumber, very stable with the growth rings coming in perpendicular to the face of the wood. All right. Here is our less stable quarter sawn boards, where the growth rings are running parallel or near parallel to the face of the board. So we have our in the summer we are both. Each board is 12 inches wide, and then in the winter, the shrinkage we see is twice the amount actually. With the plane sawn. I'm sorry if I might have made a mistake referring to that. This is our quarter sawn. This is plane sawn. So the plane sawn we see shrinkage of 1/4 of an inch. And then in the quarter sawn, we see shrinkage of only 1/8 of an inch. All right, so that, and we could kind of see that in the dashed lines. It's kind of showing us that. So much less shrinkage over here with the quarter sawn, but we also see here that the plane sawn is prone to cupping, kind of deforming, and that's something we definitely do not want in our floorboards or our deck boards, for instance. Okay. All right. So ideally, the lapse between the time that the tree is first cut down and the wood is used in construction will allow for most or all of that free water to evaporate, but that does not always occur. All right. Often wood is just rushed to the job site, or perhaps it's not taken care of properly afterwards. It's often bundled, wrapped in plastic, and that slows the evaporation, giving it little chance to dry until the bundles are unwrapped, and then framing might already be underway. So that could be very problematic. We do not want to install wood that is wet, essentially, or has too high of a moisture content. All right, so when it comes to drying, defects arise to uneven drying, leads to a rupture of wood tissues, checks in the surface and or internal, end splits, and honeycombing. So these are all defects, kind of just like vegetables, for instance. You could pick a perfectly great vegetable from a garden, but if it's not taken care of properly afterwards before it arrives at your table, it would be compromised. It would not be the quality that it was when it was first picked. Same with trees. After they're harvested, they need to be taken care of properly. So checks, end splits, and honeycombing are all problems that reflect not being properly dried. So aggressive drying, it happened too quickly, and we have honeycombing in the center. Term we also saw when we discussed concrete. Here we see end splitting and some other problems. So often nail pops. So if wet timbers are installed and then they dry out, they could actually force the nails out, and that we could have drywall pops, they would call that. And here we see a popping nail on the roof as well. So it causes a stress, an internal stress inside the wood, and the nail pops out. On the extreme side, mold. And, of course, painting or staining. So low permeability paint can prevent water. From exiting the wood. So we need to have our wood properly finished, of course, before it is ever painted. Very important. Okay, so moisture content versus compressive strength for some particular species here: red spruce, longleaf pine, and Doug fir. So this chart reads a little counterintuitive to me. It kind of starts on the right and reads to the left. So here's our moisture content, and it starts high and then it decreases. So I'm not sure why this chart wasn't mirrored so it reads this way exactly. And here's the compressive strength. Lowest at the bottom, greatest at the top. So as it dries, its strength increases, which is what we have been saying. I think this chart would read a little more clearly if we were starting here and growing in that direction, but the point still is relatively clear. Okay, so that is moisture content relative to strength. Moisture content decreases, strength increases. All right, these are important. Two important charts coming up here. So North American hardwoods and North American softwoods. All right, and we will go through and discuss each of the pieces along the top. So across the top, we have different types of strength, things, characteristics, mechanical properties, structural properties that fall under the big umbrella that is strength. We know that strength is a big, broad, kind of vague term. There are very specific types of strength, so we'll discuss what those are. And then here are the species. So here are the North American hardwoods. Okay, and then so they have a specific gravity, compressive strength, bending strength, stiffness, and hardness. And the same for our softwoods. Okay, so I'm going to go through describe the types of strength first, and then we could circle back to the charts actually. So specific gravity, let's just go right to, let's actually go through this. So we'll discuss specific gravity in the next slide. Compressive strength, so just they're talking about how things are loaded relative again to those important vocabulary terms. So loading a block of wood parallel to the grain. So this would be a column, right? We know that's how columns are loaded. They function with compressive strength. So a wall stud also would be loaded in such a direction or manner. So bending strength would be loading it perpendicular to the grain, which would be, of course, a beam, right? The axis of the beam runs horizontally, but they are loaded from above, and that would be perpendicular to the grain of the wood. The grain of the wood runs with the axis. So in a column, the grain and the axis run vertically, north and south. In a beam, the grain and the axis run horizontally, or east and west, so to speak. Okay. Stiffness, we know, is a term from our stress-strain curve, and that is the kind of a strength that is pertains to a material in its elastic stage. So that is when our floor joists are being loaded but kind of bouncing back. So no permanent damage has occurred, and it's just a kind of a measure of that strength, and it's taken from the stress-strain curve, and it's of course the slope of the early stage of the stress-strain curve. And then hardness. So that is driving a metal ball halfway through a wood surface, and we'll talk more about that in a moment. Okay. So specific gravity or density, very, very important quality. So specific gravity is the ratio of the density. So mass of the volume of a substance to the density mass of a same unit volume for a reference substance. So it's basically comparing two different things. It's comparing typically specific gravity is a measure of water. So how dense is the mass of a certain material relative to waters? So water, we say, has a specific gravity of 1, and then we compare things to it. So balsa wood, we know, is that very soft, light wood that's used in architectural model making. It has a specific gravity of 0.2. So it is 0.2 times as dense as water. So water's a lot more dense than balsa wood. Aluminum has a specific gravity of 2.7. So it's 2.7 times. So aluminum's a lot more dense than water. Lead, much more dense yet. Mercury, more dense. So ipe, wood, is one of very few woods that is actually more dense than water because it has a specific gravity of 1.08. So ipe is one of few woods that will actually sink and not float. And that is a very heavy, very dense wood that is used often in boardwalks. It's found in South America, and unfortunately a lot of not very sustainable practices in terms of harvesting it. But it is a very strong, very, very dense wood. And so here we could see this chart is really not particularly helpful. It doesn't even tell us what we're exactly measuring, but it is showing just how the relative density. So ipe is significantly more dense than oak, and we typically know how heavy and dense oak is because that's a common wood that we see more often. Cedar, very light wood. Okay, so density is the single most important indicator of strength in wood. All right, so basically the heavier it is generally means it is the stronger that it is. So if you had to choose a wood based on one particular quality, density would be the one that you would want to choose. All right, compression. So shortens. So compression strength shortens or compresses material. Right. So here is compression, 2 arrows coming in. So that is how we load columns typically. Right, standing up and down. Force pushing down on the column, something pushing, or the ground or the foundation pushing back up on the column. So for the woodworker, the primary types of compression to consider are parallel to the grain or perpendicular to the grain. So very important. So wood, different from concrete, different from steel, is again, of course, a natural material, and its properties, its behavior is different relative to the grain. Okay, so compression parallel to the grain shortens the wood fibers lengthwise. So parallel to the grain would be loading it like a column, right? The column runs up and down. The wood fibers run up and down, and the load on a column comes directly down on it. So that is parallel to the grain. An example would be chair or table legs, which are primarily subjected to downward rather than lateral pressure. So a chair or table leg is essentially a small column. And we see that here. So wood is very strong in compression parallel to the grain, and it's seldom a limiting factor in its design. So that is not a problem with our chair or table legs. It is considerably weaker in compression perpendicular to the grain. So perpendicular to the grain would be the floorboards. So this point load is coming down on that floorboard perpendicular to this grain. And it is in compression, right? It's experiencing compression. This chair leg is pushing on that floorboard perpendicular to the grain, and it is not nearly as strong as it is when loaded parallel to the grain. So the geometry and the understanding of which direction the wood grain runs is very important. Okay, now we are looking at tensile stress, which we know pulls an object apart, elongates or expands it. So here we see tension, right? Two arrows going in opposite directions. So perpendicular to the grain, tensile stress perpendicular to the grain, quantifying resistance to splitting. An example would be splitting firewood, as we see here. So this, I find this confusing, this example a little confusing, or I don't know, maybe a little counterintuitive reading it. The former slide, the previous slide, was a little more clear to me. So the grain is running up and down, but it is being pulled perpendicular to it. So I guess just because the axe is coming down, the axe is actually coming in parallel to the grain, but the splitting that is occurring is perpendicular. So the forces are coming out in each direction, left and right, even though the force that's being applied to it, the axe, is coming down parallel to the grain, but it is being split, pulled apart perpendicular to the grain. But it is very strong in tension parallel to the grain. So if you were pulling a piece of wood apart, it would be much easier to pull in this direction, pulling it left and right in this direction as visualized here in this image, as opposed to pulling up and down. So perpendicular to the grain, it is weaker. Okay, so coming from the modulus of elasticity, so the material stiffness indicates how much the wood will deflect when a load is applied. So we know that the modulus of elasticity and stiffness stems from the stress-strain curve, from the elastic portion of it. So we have our stress-strain curve, and while we're in the elastic region, we have that straight line coming up, and the slope of that line tells us about the stiffness of a material. And of course, it's in the elastic region, which means it bounces back, and that's what deflection is all about. So when something deflects, when we walk across the floor and the wood beams deflect and push down a little bit, has a little bounce in it, that is deflection. And then when we get to the other side of the floor, and the load is off of the beams, it returns back to its previous state. So that is, by definition, the elastic state. And so that is what stiffness is a measure of. So how it is, how much it deflects when load is applied perpendicular to the grain, because that is typically how joists will be loaded, of course. Otherwise, it would be a column. So we're walking across the deck, and this beam is deflecting a little bit, perpendicular to the grain. The load is coming down perpendicular. That's what we see here, loaded perpendicular to the grain. And then finally, the hardness test. So this is resisting indentation or abrasion or scratching. So a very important consideration for wood floors. So basically, they drive this steel ball into it. So it's less of not so much a structural test, but a kind of a resistance to denting, which is, so wood floor is not really a structural member per se, but still for finishes, obviously a very important characteristic. So just to return now back to the the charts, so we discussed density, specific gravity, which is also a measure of density, compressive strength, bending strength, stiffness, and hardness. So we've discussed all 5. So what one should be able to do is, if you were asked which North American hardwood is best suited as a column, you would know that you would have to be looking for compressive strength, and we would run down this chart and we would find the hardwood that has the greatest compressive strength. So we see 7,400, 74, 92 for hickory. So it looks like hickory would be the winner. So hickory has the greatest compressive strength, so therefore it is the best suited to make a column. If we were looking for a floor that is most resistant to abrasion, we would want to look at hardness. And likewise, we would come down here, and here is 1450. That looks like the winner in that category. So hard maple would be the answer to that. If we want to jump over to the softwoods and we wanted to talk about a beam, and we would think of bending, then we would come down this column and we would see that 12,400 and Doug fir would be the best suited to build a beam. Okay. Overall, if we were looking for an overall strength, we would think about density and specific gravity, and we would come down here and we would see, I think again, nope, here we go, yellow pine, 0.59. So the most dense of the softwoods is yellow pine. Let's just jump back one and see how that compares to the hardwood. So we had 0.59 right here. Ash already has that beat. Beech, better yet, 0.64. Hickory, 0.72. So again, it looks like hickory would be the winner, unless I'm overlooking something. So hickory is the most dense wood. So as an overall guide to strength, we looked at specific gravity and density, and hickory out of these 2 charts would be the winner. Ipe is not on the chart, so that would beat hickory. Hickory is what baseball bats are typically made out of, so a very, very dense wood, of course. Okay, so moving on. So one more chart here. Again, these charts are not identifying what exactly they're measuring, so it's just relative hardness. So this would come back to the Jenka test, just telling us that Brazilian cherry and mesquite are both particularly strong, where our softwoods that we use for a lot of framing materials, such as Doug fir, they have their strong suits, but hardness is not one of them. They dent very easily. And if you've ever worked with dimensional lumber that we find at our typical homes or Lowe's or Home Depot, you know it is to the touch kind of a very soft wood relative to our hardwoods. Okay, let's look at bending strength in wood. Okay, so in wood, the extreme tensile stress is substantially greater than the maximum compressive strength. So we know that beams experience, a simple beam that is, would experience compression at the top and tension at the bottom. The greatest amount of compressive stress is at the very top face, and the greatest amount of tensile stress is at the very bottom face. And what this slide is pointing out here is that the tensile stress is the breaking point, essentially. That is, it experiences much greater tension than it does compression. So the tensile stress would be the limiting factor. With knots and other imperfections in that tensile zone, failure in tension typically occurs first. So down at the bottom of the beam, knots would further compromise the strength, the tensile strength. Okay, the bending strength, like compressive and tensile strength, is influenced by several factors. So the unit weight of the wood, the moisture of the wood, which we've discussed in detail, the direction of the grain, we've also discussed, and knots, which we know are imperfections and affect the structural potential of the structural member. All right, so bending strength is affected by all of these things. Okay, different from bearing strength. Okay, so bearing strength is, we're seeing right here. So bearing strength refers, when we talk about bearing, it's when one structural member lays right on top of another. So that would be the bearing surface right there. And the bearing strength of the wood would be its ability to resist this crushing that we see occurring in this illustration. So, related directly to the crushing strength of the fibers. So bearing strength and crushing strength are kind of synonymous, and they are related to the timber fibers, which is a function of the species. All right, so going back to that chart, that would be talking about the density, basically. And it's basically influenced by the thickness of those cell walls. Okay, so density of timber is also a function of the thickness of cell walls. So density is a good indicator of bearing strength. Okay, so the more dense, again, going back, we were talking about the hickory, a very dense wood be much less likely to be crushed than the Douglas fir, for instance. Okay. But interestingly, it does not appear to vary much with the grade of the timber. And we talked about all of those factors that go into the grade, such as the knots, the firmness with which the knot is held in place, for instance. Those characteristics tend to lower the grade of the material, but they do not actually have a big effect on the bearing strength. And this next slide points out here that basically a sound knot, one that's intact and not falling apart, basically, have generally a higher density and a higher bearing strength than normal wood fiber. So a knot, while very detrimental to the tensile strength in a beam, for instance, would not affect the bearing strength. You're much less likely to actually crush the knot. First, the actual wood would be crushed, but the knot would not. All right. So the knots do not compromise the bearing capacity of a timber. All right, so again, a living organic material is, much more peculiar than concrete and steel, man-made. All right, unsound knots. So an unsound knot are ones that have cracks or voids and would be softer than the surrounding wood. And so these, we see a lot of voids in there. So these would be unsound knots, as opposed to this one that we saw here, a solid sound knot. All right, and the direction of force also does affect the bearing capacity. So here the wood grain is running, so this would be a beam loaded perpendicular to the wood grain, experiencing compression perpendicular to the grain. This would be a column loaded in compression parallel to the grain. All right, bearing or crushing capacity is significantly stronger parallel to the grain compared to it perpendicular. So bearing or crushing less likely to occur in the column, more likely to occur in the beam. So in this photograph, if asked which structural member and at which location would we expect crushing to occur, it would be in this girder, potentially right here where it's sitting on the column. It could be in the joist or the girder right at this location either, because these forces are coming in perpendicular to the grain, right? This joist is coming down and bearing on it perpendicular to the grain. This column is pushing up on this girder perpendicular to the grain. This column is being bared on, however, parallel to the grain, so less likely that this column is going to crush here. That girder would be crushed first. Okay? And here we see crushing, or bearing failure right there. Okay, so bearing both parallel and perpendicular to the grain is a fairly ductile phenomenon as opposed to a brittle phenomenon. So brittle, again, we think of ceramics and glass, things that break very quickly. Masonry, very brittle. But when failure like this occurs, it does not occur quickly. It occurs slowly over a period of time. As more fibers get crushed, they squash outwards, loading an even greater number of fibers. It's rare that these types of failures will collapse in a first instance. So a slow failure. However, excessive crushing during bearing failure has the potential to change the load transfer path and lead to overloading another structural member. And that's also a big concern I think we've discussed in seismic events. When an earthquake occurs and buildings shift, load paths sometimes transfer, and non-load bearing structural or members, building members that were originally not part of the structural path are now taking on structural weight, and that could be very dangerous. And in some cases, it points out here that bearing is not available for inspection. Often all this framing, especially in wood construction, such framing, dimensional lumber is covered by drywall and siding, so we can't see it. So a substantial amount of damage could go unnoticed until something actually is destroyed and collapse follows. Okay, thank you, and I hope you enjoyed that.